This is the future of AI data centers. Every second, we feed oceans of data into silicon brains. We demand faster answers and agonizingly complex AI. But intelligence has a physical cost, which is heat. Today's data centers are digital furnaces. They consume vastly more electricity than entire nations, fighting a losing battle against terrestrial thermodynamics. We are boiling the very air we breathe just to teach machines how to think. To break through, we have to leave the atmosphere. We have to move the digital furnaces to the one place with unlimited solar energy and near infinite cooling. This is the engineering blueprint for unlimited intelligence. To understand why we are leaving Earth, you have to look at the energy bill. Right now, a single hyperscale data center consumes as much electricity as 50,000 homes. By 2030, AI training clusters could devour nearly 4% of the planet's total power supply. It isn't just about electricity, it's about water. On Earth, to keep high-end GPU clusters from frying, we evaporate millions of gallons of fresh water every day for cooling. We are literally drinking our reservoirs dry to power our algorithms. The physics of Earth are working against us. Our atmosphere traps heat, and our rotation cuts off solar power for half the day. But just 100 kilometers up, the rules of thermodynamics change completely. Space is the only place where energy is truly free. In a sun-synchronous orbit, a server farm never experiences night. It sits in 24 hours of unfiltered sunlight, bathed in solar intensity 10 times stronger than what we get on the ground. Then there is the cold. While space is a vacuum, it offers a unique thermal advantage called radiative cooling. You don't need massive fans or water pumps up there. You simply point your radiators at deep space. The math is terrifyingly simple. On Earth, we are running out of power grids to tap. In orbit, the sun is an infinite battery, and the universe is an infinite air conditioner. For decades, the door to orbit was locked by a single stubborn number: the cost per kilogram. Historically, putting a pound of payload into space cost as much as a pound of gold. At those prices, you don't launch heavy copper wiring or massive steel server racks. You launch delicate, lightweight instruments. This economic reality made orbital data centers impossible. But that reality has collapsed. With platforms like SpaceX's Starship, we are moving from paying $10,000 per kilogram to potentially less than 100. We can now launch standard ruggedized shipping containers packed with off-the-shelf Nvidia chips. We aren't just launching satellites anymore. We are launching infrastructure. However, there is a catch. The speed of light. Even at 186,000 miles per second, data takes time to travel. If you put a server on the moon, the round-trip signal takes nearly 3 seconds. That makes real-time tasks, like high-frequency trading, cloud gaming, or autonomous driving, impossible to manage from deep space. This forces a new division of labor between Earth and the orbital cloud. Space becomes the factory for training. This is the heavy lifting where AI models consume petabytes of data over weeks or months to learn. It is energy-intensive, hot, and slow, perfect for the vacuum of space where latency doesn't matter. Earth becomes the home of inference. This is where the finished, trained model is actually used. But there is a reason we haven't done this before. Space is violent. Down here, Earth's magnetic field protects our electronics like a warm blanket. Up there, that blanket is gone. In orbit, cosmic rays and high-energy protons smash through metal hulls constantly. When one of these particles hits a microchip, it causes a bit flip. A 0 becomes a 1. In a normal computer, that's a glitch. In a sensitive AI training run, it's a lobotomy. To solve this, engineers are building triple redundant architectures. They don't just trust one chip, they run the same calculation on 3 different chips simultaneously. If one gets hit by radiation and gives the wrong answer, the other 2 vote it out. It is democracy applied to silicon survival. Then there is the connection problem. You can't run a fiber optic cable to orbit. To move the massive petabytes of data required for AI, we are switching to light. This is the optical mesh. It involves lasers shooting data between satellites at the speed of light in a vacuum. Surprisingly, this is actually faster than terrestrial internet. Light travels 30% slower through the glass of a fiber optic cable than it does through empty space. For some clients, however, the killer feature isn't speed, it's security. If you are a government or a bank, a data center in space is the ultimate air gap. There are no doors to pick, no cables to tap, no way to physically breach the server without a rocket. We are building a fortress in the sky, impervious to local power grid failures, immune to natural disasters on the ground, and physically untouchable. So, how close is this reality? We are currently in the proof of concept phase. Companies like Lumen Orbit are already scheduling demonstration missions, partnering with chip manufacturers to test high-performance hardware in the harsh environment of space. By 2035, industry analysts predict that a significant percentage of the world's most demanding AI training runs will occur off-world. The economics are simply undeniable. When the cost of energy in space drops below the cost of energy on Earth, the migration becomes inevitable. We are witnessing the start of a new gold rush. But this time, we aren't mining the ground for metal. We are mining the sky for intelligence. But data centers are just one thing. 5 other technologies are arriving in 2026, from landing on the moon to the first commercial quantum pilots. If you think putting servers in space is radical, you need to see what is happening on the ground right now. I have broken down these top 5 world-changing technologies in the video on your screen. But if you enjoyed this one, then don't forget to drop a like, and I'll see you in the next one.